Hello friends, welcome to the world of deep learning. Today we'll be speaking on the topic convolution neural network. Before we move on, I would like to introduce myself. I'm Srinidhi, a deep learning intern at ZIP. I've completed my master's with specialization in machine learning. Prior to master's, I've worked as a Java developer for 2 years. So now let's get back to the topic. Convolution neural network. So in this term convolution neural network, you have something important called as convolution. What is this about? Convolution, as we have read during our school days or somewhere during the education, is nothing but multiplication of two signals, wherein one will be a static signal uh, to get a convolved signal. The process is simple. You will have one fixed static signal with which you're going to multiply a linear signal separately. Means it will have a time difference of 1 time shift. Say here you'll have your 1 multiplied with the impulse signal, you get certain output. Then you have a 2 multiplied with the impulse signal, get certain output. But here it is that you are going to shift the signal by 1 when you're multiplying by 2, and then these two multiplication output of 1 and 2 you're going to sum it up, and what you get now is called as convolved signal. So this thing, when you apply to the world of deep learning, this is what something it looks like. You have a fixed image and you have a kernel or a filter which is going to move in each step such that you're going to get an output. Say here when you're multiplying your kernel with a certain patch of an image, you're going to get an output of 4. So this, when you do it repeated for the whole image set, what you get at the end is called as a convolved image signal or a convolved signal. But what exactly is happening during this process of convolution? So it is nothing but feature extraction. So you can compare feature extraction to that of solving a puzzle. I'm sure when you're all young, you would have played some games called as building puzzles, such that you'll be given a set of images all scrambled around, and those scrambled images you have to put it together to form one big image. This is exactly the same thing that is happening during a feature extraction stage. Say initially it is like in the first layer of convolution, you are going to detect the different type of lines. In second layer, you are going to combine these lines to form shapes of two lines, say like V, inverted V, T, L, so many. And the next one is like you have to combine these lines of ones and to form different shapes, squares, triangles, rhombus, and so on. So at the end, when you have all these shapes, you're going to fix it to one big image, which is called as a face. And this is nothing but recognition of a face. So now, what we have done is just from a set of pixels, we have actually converted them to some readable features like square, triangle, then what do you say, rhombus, diamond, such that these can be assembled to form a face. So I think we have a good understanding of low level. But how does it happen during our image representation? A simple example is as below. So we have two rows here and two columns. So when each row has two different type of filters, overall four. So in our first row, first column, the filter says that it's good at detecting the inside edges of the image. And first row, second column says it is good at detecting the outside edges of the image. Similarly, below, the second row, first column says it's good at detecting the horizontal edges, while the second row, second column says it's good at detecting the vertical edges. So what we have found is, like just from one single image, with the use of different filters, we have been able to extract different set of features. So these features, when we combine it to at the end, what this helps us in classification of images in this digits. So But convolution is not all about feature extraction. It has something bigger too, say like ReLU and max pooling. ReLU is the type of activation which you are going to choose. I'm sure you would have come across something called as sigmoid during neural networks. But why ReLU? This is because it reduces the problem of vanishing gradient descent. Say, why vanishing gradient descent? If you have a deep CNN layer, what happens is your weight update by the time it traverses from the input to the output. It would have diminished to such an extent such that at the end, when you're going to add this value to the output, it doesn't matter at all. It hardly matters. Such, in order to avoid such situations, we use ReLU, wherein what it does is, after you get a convolved image, it says if the convolved signal is negative, I'm going to clip it to say 0. If it's positive, I don't do anything, it's just left the same. But indirectly, it's also doing the job of converting linear data into form of non-linear data. So the part of sigmoid is done, and also we have also like avoided the part of vanishing gradient descent. And then we have max pooling. This is because we want to like reduce the size of a convolved image. It's not always necessary that when you're going to extract features, you do it from each and every image pixel, right? Because you know, if you're in a black region, the probability of finding black pixels is more. Therefore, it's sufficient if you can detect one image, okay, say like one pixel for every 4 pixels as black, right? Same thing. So what we are doing is for for every 4 pixels which are next to each other, we take one value among them. It can be the mean, max, or the minimum. That doesn't matter. But what matters is we are we are going to reduce the size of our image. We can do it by a still further margin, but it's generally preferred to be 2 because we also don't want to lose out on any important information. So all these concepts, when we combine together with that of a fully connected layer, what we get is something called as convolution neural network. So see, the initial part is of convolution and max pooling, final part is of fully connected layers. So these layers of convolution pooling, it actually can't be said on the uh, outset. It depends on the data set you're doing and the number of factors like what is the time you have and what is the processor speed you have and so on. Processor speed because as the depth of CNN model increases, your time of processing increases. So then if you have say some CPU, not a GPU, then it takes days, sometimes years. So it depends on many external factors and design aspects and also the data set. So you can't decide it. So all these are called something called as hyperparameters, which we'll discuss further. But one important concept is at the end, when we are going to classify the data in the last stage of fully connected layer, the type of activation which we use is called as softmax. This is because when you're using softmax, you're going to classify the data based on the probability of each class occurrence. This generally gives higher accuracy compared to using a sigmoid function. Because sigmoid, when you say for a binary classification, it's good because you say if the value is greater than zero point 0.5, take the class as 1, else take it as 0. But when you have a multi-class problem, what happens there? We'll be using one versus rest classifier, and uh, that actually leads to decrease in output accuracy. Hence the reason we use softmax. And there's another thing which I have to discuss. As you're seeing in this layers, we can see that there are lot of different networks involved. So what happens here is the number of parameters or number of the weight parameters which you are going to update, that increases rapidly. And this sometimes, when you have less number of data, leads to a problem called as overfitting. So thus we overcome this problem overfitting by using a concept called as dropout. So what happens in dropout is we are going to cut the flow of data between two layers of a neural network by a small portion, say 10% or 20%, not too much also. What this does is this acts as inducing noise to the model, and this makes the model more brainy, such that such that a model learns to classify when it has lesser number of information and its accuracy increases. This you can combine to a writing exams, wherein when you are preparing, you would have prepared for a lot of different aspects. But on exam, we do find questions wherein the answers are not so direct. Rather, we have to use our knowledge on based on what we have prepared. And there will be some trick questions wherein you get a better output and the results you have to solve it. So there is something related to that, wherein you use your previous knowledge to classify the data. So this other concept is called as hyperparameter grid search. So this hyperparameter grid search is used because CNN definitely has a lot of different hyperparameters, and you can't on the onset guess it what is good for what. So we use something called grid search, wherein we choose two or three hyperparameters uh, of different values, such that when we train it, we get to know the best combination. I've used two hyperparameters, filter size and dropout, and I've got the answer as for a filter size of 5 and dropout rate of zero point 0.1. My model is best designed. We can try it for different hyperparameters like weight initialization, type of activation, number of convolution layers, number of filters in each layer, and so on. But this is all like guessing method, so there's no best approach. But this actually, if you do a grid search, it's good because it will reduce your training time, or you can decide earlier on what is the best model rather than trying each time by different combination. You can try it at once. So the best model which we found was like this, wherein we had two layers of convolution with one layer of dropout, one layer of fully connected layer with the concept of dropout use device. So as you see, we have an convolved image, and the input image size varies. And this is because of the obvious reason of filter traversing. And in a general, you can say a convolved image size is equal to the input image size minus the filter size plus 1. 28 minus 5 plus 1, 24. 12 minus 5 plus 1, 8. So this is something which should be good for you to remember. So RCNN applications are like video analysis, image recognition, and NLP, natural language processing. But generally, it is used in the field of image recognition and video analysis. Video analysis in turn is actually a mixture of CNN and RNN. We'll discuss more about RNNs in the future. Hopefully, you have got a good understanding of what the CNN is. And so like after going through the video, if you have any doubts, please feel free to ask me here. I will respond as soon as possible. And the other thing is like if you want to know more about the projects I've done, please visit my website. You can find the different projects I've done there. So looking forward to see you in my next video lecture. Till then, thank you.